Fancy meet computers. How's everybody doing on this, our second straight day of terrible rain and grossness in general, at least in this part of the world? If you're living in a part of the world where things are sunny and beautiful, do us all a favor. All of us, do all of us who live in Ontario a favor. Just, go outside and enjoy the sunshine a little bit on behalf of all of us. We would really appreciate it. Take pictures. Send us the pictures. How is everybody doing today? It seems you guys had a midterm yesterday, which sounds like it was kind of an ordeal. Oh, my smokes. We need to keep moving on this material for sure. Okay. Good. So I did binary search. This is good. I used a recursive method. Yeah, okay. Let me check to see if we have any announcements. Nope, no announcements. Yeah. Well, I realize that Halloween is like a holiday in theory, but I guess it is I don't know. I guess it's like welcome to adulthood, Halloween is primarily a holiday for children. But, I know that's sort of scant consolation, but, So, we have to actually, we're a fair amount behind on these lectures, so I'm just gonna plow through these today. So, if I'm going too fast, watch it back slower. So, okay. So, last time we were doing the binary search algorithm. Somebody made a bet with me that I couldn't get it in first try, and I got it first try, and now he owes me 20 bucks in Bitcoin. Actually, I was the bigger person, and I said, nah, don't keep your Bitcoin. By forgetting what my wallet ID was. Although that's also true. But anyway, so, we did the binary search algorithm. This was a, it was, just to remind ourselves, the binary search is where you have, the whole search space of the entire array. You chop it in half and make a decision about where the thing you're looking for is, because of the value of the middle element of the array, right? If the element that you're looking for is higher than the middle element, then you know it must be above that element in the array, and conversely for the lower half. This only works on a sorted array, however. So, binary search using recursion is much faster, because it only has to look at a small number of items in the list. Technically speaking, you don't have to use recursion to do this. It's technically true that you don't have to use recursion to do anything, and you don't have to use a loop to do anything. You could use recursion instead. They're interchangeable methods. It's just a matter of what's easier in using which method. So, you can do binary search by just keeping track of indices. Keep track of several indices and update them. But it's also possible to use recursion. Yes. If the list has a length n, then the binary search using recursion looks at approximately log base 2 elements of the list. This is a very, very good runtime. It means that you can search 1,000 elements in 10 steps, and you can search 1,000,000 elements in 20 steps. Approximately speaking. And, it just goes up from there. So keeping your data sorted is extremely useful. The next version, the version on the previous slide is somewhat inefficient because it creates a new list every time by slicing. Next slide shows binary search using recursion by keeping track of start and end points of the sublist rather than making a new list each time. So, rather than... see how this one creates a new list by slicing and passes that back? That's one way to do it. That consumes a bit more memory, although using this memory you will never consume, in addition, more elements than the array originally had in it, so you're doing no more you're no more than doubling the amount of memory that's occupied by the array originally. How noble. Yeah, well, you know, it's kind of it'd be kind of terrible for me to take your money, you know. I'm already taking your money in tuition, so. So, this is binary search using a helper function. So I bet a lot of you didn't know this before this slide, but you can declare functions within functions. When you declare a function within a function, that function is scoped to the outer function. So search3 helper does not exist outside of the context of search3, which is kind of interesting. So the thing that it's doing here is it's using low and high. Basically, search3 helper is search3, but with two added parameters, low and high, which keep track of the upper and the lower bound. And you can see that we are returning search3 helper with 0 and the length of n as initial values. Now, I would argue that this is a highly inefficient way of doing this. The better way of doing this would be to make high and low default parameters of the search3 function, which would allow you to set, you know, low to 0 and high to the length of L. Although I'm not sure if you can do length of L inside of here. Might be worth investigating. That might be the wrench in this. That might be the spanner in the works right there. But yeah, so you can use sub functions to help you out with other functions if you so choose. Notice how we define one function inside of another. Yes. Functions as objects. In Python, functions are first-class objects. This means that we can use functions like objects of other types. In particular, we can pass functions as arguments to other functions. This is why we say in Python we say that Python can behave like a functional programming language. It's not a functional language. It's a multi-paradigm language, which is a fancy way of saying that it steals ideas from other languages. But yeah, you can have it behave in a quasi-functional manner, although if you're really going to need a functional programming language, you should use Haskell. Question: is there benefit to defining functions inside of functions? Well, what it does is it prevents any other part of your code from wanting it, or not wanting it. It prevents any other part of your code from needing it. So it's kind of like it's like restricting your permissions, right? It's like the only function that could ever have use for this function is the one I've put it inside. There's no reason for anybody else to need to be able to have it. Once we start getting into... It's kind of like advanced territory at this point. Like, you guys shouldn't have to worry too much about, like, public, private, static variables, that kind of thing. Especially in Python, because Python kind of doesn't like permissions to some extent. You know, if Mark's in the chat, he's going to jump in and say, but. But that's my general impression of Python, is that, like, permissions are not generally a thing that it cares about. So, yeah, so that's why you would do it, is to restrict access to the subfunction. So, good. Passing functions to functions. Those of you who are in 1JC3 and are doing Haskell may have already seen a function called map. Map takes a list and it applies a function to every element in the list. It's actually, like, as a person who's done quite a bit of Haskell programming in the past, my thesis research, map is one of the sort of workhorses of functional programming. You use it quite a lot if you're doing anything, you know, of any considerable size. So in Python, what that looks like is you take a list, you take a function as an argument, f, it's usual to denote the function as f because, you know, functions, right? For I in range from 0 to the length of L at I is equal to f at L at I. So basically, we are taking every element of L, applying the function f to it, which has been received as an argument to the function, and then storing that result back in L. So, for example, we could import math. We have a list 1, 2, 3. We could map math.cos, that is cosine, over L, and then print it. For assignments, can we call other functions not already in the assignment in the new function we are writing to solve the problem? You can do that to an extent. You're free to use standard libraries, but like if I'm asking you to produce a sorting algorithm and you just call the built-in sorting algorithm, you'll probably be disappointed with how many grades you get. Some questions have a blacklist of functions, but if it has a blacklist, that will be obvious. So, anonymous functions. We can also make anonymous functions right when and where we need them. You don't have to worry about this too much, but this is the equivalent of Haskell's lambda. Essentially, if you write lambda, you give some variable names, and you have an expression. This is the so-called argument extraction operator, also known as the abstraction operator. So, if you have lambda x and y for x to the power of y, that becomes a function that you can apply 2 arguments to. So, let me just demonstrate this very quickly. Wait. Not preferences. There we go. So, if, for example, I say lambda x, y, x to, to the power of y, that's a function, right? If I then take that lambda and I apply arguments to it, say 4 and 8, it calculates 4 to the power of 8. Or 2 to the power of 8. You might say to yourself, well, this seems kind of trivial. Why would you go to all of this length when you could just type 2 to the power of 8? Oh. That's 2x over 8. Sorry. There we go. 2 to the power of 8. And the answer to that question is you've got, like, there are lots of things you can do with lambdas. Like, it doesn't just, you don't have to abstract every element of this expression. You can leave parts of it, like, unallocated. For all of the interesting uses of lambdas, I would refer you to the Haskell programming language. I would also tell you that lambda expressions in and of themselves are Turing complete. So it is possible to write every single program that has ever existed purely in pure lambda calculus, which you'll see when you take 3MI3 with me if you get that far. So, yes. So one thing that you can do with them is you can plop a function as an argument to a function without having to give that function a name. But yeah. What does Turing complete mean? It means that it's equivalent to a Turing machine. It's got everything in it that is required in order for it to be Turing complete. So hopefully you all know what a Turing machine is. Hail Alonzo Church. Yes. Hail the Church-Turing thesis. What is a Turing machine? Oh my goodness. Okay. very brief tangent. I'll see how quickly I can explain what Turing machines are. So, the Turing machine is one of the earliest models, like mathematical models of computation that existed in these were the Turing machine was developed as an idea by a man called Alan Turing, who is the granddaddy, one of the granddaddies of computation as a science. The idea is that you have a tape, right, an infinite tape with symbols on it, and that you have a read head which can read a symbol, write a symbol, or jump to another position in the tape. The important mathematical work that Turing performed was he proved mathematically that all equations which are computable via a Turing machine. His PhD supervisor was a man by the name of Alonzo Church, who came up with a similar result for the lambda calculus, which lambda calculus is something that we'll talk about to some extent in 3MI3, if I'm still teaching it by the time you get there. Well, it's usually covered in that course, whether or not I'm teaching it. But yeah, so lambda calculus, I don't have the time to get into how it works, but there are only two operations in lambda calculus: function abstraction and function application. Everything else, so you can compute anything you need so long as you have those two in a pure lambda calculus. Now, it takes a very long time to do anything in pure lambda calculus. Normally, we enrich it with other, your standard suite, of arithmetic operators, but the point is that you can do it in pure lambda calculus, and that lambda calculus is, lambda calculus can do anything that a Turing machine can do. So, since we have a proof that Turing machines can perform any computation, we can therefore conclude that lambda calculus can perform any calculation. And the same is true of Markov chains. I don't know that much about Markov chains, so don't ask me. So, topic 6, numerical computations. We're going to talk about how numbers are represented inside of your computer system. So, let's talk about the integers. I'm assuming all of you know how a decimal number is represented in normal math. You have each place value being multiplied by 10 to the power of whatever the place is minus 1, right? So 3 times 1, 5 times 10, 0 times 100, 2 times 1,000. That's how number representation works in the decimal system. Well, it turns out that in the binary system, things work very, very similarly. This is how binary numbers work. It's important to remember that all, underlined, underscored, italicized, all caps, everything in a computer fundamentally is represented as a sequence of ones and zeros. This is because at a fundamental level, at a hardware level, electronically, every number numbers are represented in electronic circuitry by either a high or a low voltage. Depending on the electronic device, high could mean anything from 3.3 volts to 5 volts to 20 volts if you want to get to high-end stuff. So high means you have some voltage. Low means you have 0 volts, relative to the potentiality, relative to whatever the electrical potential of the entire device as a whole is. So the ones and zeros, 0 is low, 1 is high, you have sequences of either registers or memory cells which hold on to their state. They hold on to either a low or a high voltage persistently. So numbers are built from these sequences of ones and zeros. So we represent numbers in the binary system in the same way that we represent numbers in the decimal system, we just modify what the base is. Binary numbers have 2 digits, 0 and 1, right? Whereas in the decimal system, you have 10 digits, 0 through 9, right? So this is how that works. So you have 1 multiplied by 1, 0 multiplied by 2, 1 multiplied by 4, 1 multiplied by 8, in order to come up with the actual numeric value of the number itself. No, this isn't on the midterm. This isn't on the midterm. So in base 10, that would be 13, right? But in base 2, it's 1101. This is kind of that very old programming joke. There are 10 types of people in the world: people who understand binary and people who don't. So I'm gonna skip the quiz. Basic approach. So if we want to compute the sum of the relevant powers of 2, if we have some binary number, the generalized equation is we have the first one, be it 0 multiplied by 2 to the 0, be it 1 multiplied by 2 to the 1, etc., 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 until you've multiplied every binary digit by the corresponding power of 2. This is slightly... Yes. Yeah, we're going to get into mantises when we talk about floating point representation. It's a little bit tricky to do this in Python because, unfortunately, the way that Python represents binary numbers, I can't believe that Python does it this way, but this is how Python does it this way. It does it as strings. Python represents binary data as strings for some reason. I don't know why. Sometimes I look at Python semantics and I'm like, did they do this just to annoy me? It covers up to the midterm covers up to the end of topic 5. You'll have some recursion on it. But yes. Yeah. I don't know why they do it. I don't know why they do it. It would be so easy. The computer wants to be able to represent binary numbers natively. I don't know why they represent it with strings. But anyway, so if you have a string of 1s and 0s, the way that you convert that to a decimal number, to a base 10 number, is via the following algorithm. So you initialize it to 0. For I in range, the length of the sequence of binary digits represented as characters. If b at I is equal to 1, then you add 2 to the power of the length of b minus 1 minus I. So essentially, because you're either multiplying by 1 or 0 each time, you don't actually have to, you don't have to multiply the value of the digit. You can use an if statement to do the same. This is slightly easier in Python land because, of course, these are characters and not actual numbers, so multiplying them doesn't make any goddamn sense. Yeah. Well, the thing about binary numbers in a programming language like C is that in C they also put 0b in front of the binary number. However, there are no quotes because that's just telling C, hey, this is in binary. You can do the same with hexadecimal. 0x gives you a hexadecimal number. So, starting with the leftmost digit, the accumulator is multiplied by the base, and the next digit is added. So there's also Horner's rule. So you can perform this interesting calculation where you basically just add 1 at the end and multiply it by 2. It's kind of like a left shifting operation. But yeah, if you take the number, add 1 or 0, multiply by 2, add 1 or 0, multiply by 2, add 1 or 0, multiply by 2, eventually that'll also work. So, if, on the other hand, we wish to convert from decimal to binary, for converting a number to a series of digits, the remainder of the division with the base gives the least digit, This is repeated with the quotient until the number fits into a single digit. So basically, see if it's even or odd. If it's odd, take the 1. If it's even, don't do anything. Or take a 0. Don't not do anything. Take a 0. And then divide the whole thing by 2, rinse and repeat until you've run out of digits. The easy way to do this is int some number base 2. Int can't convert non-string with Oh. Sorry, yeah. I'm doing it the wrong way around. There you go. That's how you can convert a binary number to integer using Python quickly. And I think bin works the other way. I might be wrong, but nope, there it is. So if you want a Python function which converts an integer to a binary number, it's bin. And if you want to convert a binary number to an integer, you have to specify that it's base 2. Just like with this guy, if we had a hexadecimal number, and I know we haven't done hex yet, but you know, base 16. There you go. You can convert hexadecimal numbers as well. Come on, you guys are doing computer science. You have a knack for logic. You can handle a double negative, right? Skip the quiz, skip the quiz. So this is how you would do that if you were doing it as an algorithm, and if you were putting it in a string, because this is Python. So yeah, and then you convert from decimal to binary in the same way, or in the reverse way. So there you go. So, we also have, why is everything in caps? Oh, it doesn't have to be. It's standard. The standard for hexadecimal numbers is to do them in. It's like conventional to do them in caps, but you don't have to. You know, upper or lowercase works. I was just doing it using convention. So. We also, in addition to binary numbers, we have octal and hexadecimal numbers. The PowerPoint group. All right, this isn't a PowerPoint, dude. This is LaTeX. Thank you very much. And it's because I had TAs do this for me the one summer. I had them convert it to LaTeX. So this is a matter of, if you want something done right, do it yourself. So, octal. Octal is base 8, as you might have guessed from the name. So your digits run from 0 to 7. So the reason that octal exists is you have a problem with decimal numbers which are being encoded in binary language, right? Basically, there's a problem where the decimal numbers don't fall neatly along the division lines of binary numbers, right? You can see this reasonably clearly if I convert, for example, something. Oh, it's yeah, there. So. So, the binary notation for the number 9, 9 is 8 plus 1, right? So it's this digit plus this digit, that's 9. If I go, so that's the maximum decimal digit. If I want to represent 10, right? It gets, you have to do 1010. So the problem is there are certain applications that you'll find where you need to have digits with their own bit representation. Like, you need to divide up the number by digits, right? So that would mean that you would need, in order to represent the number 99, this is called binary coded decimal. Although this is correct in, basically, if you needed to do binary coded decimal, you would need to have, like, a sequence of these guys all listed out. And you're wasting space, right? There are a bunch of bit representations that don't actually map to anything in binary coded decimal. Like, for example, 1101, which is 13. That's not, like, that's more than a digit, right? Now, most of the time the computer doesn't care, but there are certain applications where it does matter, particularly embedded systems. Yes, thank you. So, with hexadecimal, you don't actually waste anything, and with octal, you don't actually waste anything. It allows you to have a representation where, like, you can represent more than one bit at a time without losing any bit accuracy, right? So octal is 3 bits, and hexadecimal is 4 bits. So hexadecimal is base 16. It has digits from 0 to 15, and once you get past 9, the digits become A, B, C, D, E, and F, right? Hexadecimal is vastly the more used of the two of these formats. You'll see them, for example, when we talk. You saw them when we talked about aliasing and memory addresses. Memory addresses are typically represented in hexadecimal because if you were to represent it in binary, it would be too long for it to be any use, right? So if I have a list, right? If I do ID list, if I check that out in hex, I get a number that is reasonable to read. If I check that number out in binary, it's just way too long for a human to read. That's why hexadecimal is generally used. So yeah, hexadecimal. Not to be confused with the villain from the 90s television show Reboot, which, if anybody hasn't seen Reboot, you should watch it because it's hilarious 90s action. What is the ID function? That just shows me what the memory address of the data structure is. It's kind of like an address of operator in C, but you'll see what it's not important for this class. So yeah, I mean, hey, it might, like, you gotta admire it. Like, Reboot was actually one of the very first computer-animated television shows. Like, historically speaking, I believe it is either the first or one of the very first computer-animated television shows. It's right up there with VeggieTales. Anyway. I mean, you should watch Reboot just for the computer puns. So let's shift gears slightly and talk about fractional representations. Isn't there a mistake in this slide? There is a mistake in this slide. Thank you for noticing. Again, this is another instance of if you want something done right, you'd have to do it yourself. Yeah, the base 10, these should be 10s, basically. So, this is how we represent decimal numbers, right? We put a decimal place, and then we start doing the bases in negative powers of whatever the base is. So this should be 10 to the power of -1, 10 to the power of -2. This is why this is called tenths and hundredths, because this is 10. 10 tenth, right? So that's how we do decimals, which you should already know. Turns out that the way that you do, or get better students to do it for you, well, I would never ask anybody that I wasn't also securing, securing money for to do something like that, because it's tedious. And it's actually work. But anyway, so in binary, you have the same kind of idea. You can put a decimal point, and anything past the decimal point to the right exists in negative powers of 2. Of course, the difference is, with this, we have 2 to the 1, 2 to the negative 1 is 0.5. 2 to the negative 2 is 0.25. 2 to the negative 3 is 0.125, etc., etc. It's actually better to think of this as fractions. Yeah, if I paid them, they should have done it better. Yeah, well, see, here's the thing, right? Go read Niccolo Machiavelli's The Prince and read why you should never trust mercenaries. I think I'm losing my grip on this class, but anyway, so this is how we would represent a number in binary. But this this seems fairly restrictive, right? It's like we can only represent numbers which are essentially fractions, where the denominator is some power of 2, right? That's what that means. Like 0.25 in base 10 is 1 over 4, right? We can represent anything. So essentially, we can only represent things with exact precision using the binary system that are some fraction, some numerator over a denominator that is some power of 2. So how would we actually go about representing something like 0.1, which is not, it's 1 over 10, right? That 10 is not a power of 2, and it can't be coerced into being a power of 2 either. So, basically, we have to get there by increasingly close approximation, right? So, if we have 3 digits to do it, we can get 1 over 8, which is 0.125, which is, not huge. If we had 5 digits to represent it, then we could get to 1/16 plus 1/32, which is 3 over 32, which is 0.09375, which is closer, but still not there, right? If we had 9 digits to represent it, it would be 0.000110011, which is 51 over 512, which is 0.9960935. To answer your question, I always assumed binary was just for computers and humans didn't need to know how they worked. Well, that's true if you're not a programmer. Well, it might also be true if you're a Python programmer. Sooner or later, you're going to run into these types of issues. Like, representation-based bugs are the worst bugs to try to find, because you'll have no idea why you're not getting the correct result, and it's because of something, because you're not doing something appropriately with floats. The most common thing is to perform exact equality comparison over floating point operators, and the whole point of this section is to show you why you should never do that. So how do we actually represent precisely 0.1 using binary fractional notation? You can't with a finite series of digits. If you had an infinite series of digits, you could do it. It's kind of like, everybody knows that if you enter 1 divided by 3 in your calculator, you get 0.333333333, and it just fills the calculator screen, right? That's because 1/3 does not have finite representation in the decimal system. In the same way, 1/10 does not have finite representation in the binary system. Well, and it's like, so this is fine, you know, clearly computers work. This isn't a game, this isn't a deal breaker with respect to computing. But it does mean that you have to be careful about floating point numbers, because they will very often not be exactly what you think they are, unless it's perfectly unless it's like perfectly falls on something that's, you know, a numerator over a power of 2. So, skipping the quiz. So, 3/4 is represented as 0.11 in base 2, which means it can be represented with finite binary precision. 1/3, however, would be 0.0101010101, etc., etc., off to infinity, so you have no finite binary representation. Following the IEEE standards, Python uses 52 binary digits to approximate 16 decimal digits. So you can actually pull back the curtain and see what numbers look like under the hood. So format. (0.1) with 60 digits. So you can see that 0.1 is accurate up until around the 15th or 16th decimal place, right? After that, you get this very long sequence of numbers which are essentially garbage, right? The same thing happens with things like 1/3, right? The only things that you can represent with finite precision are things with some power of 2 as the base, because it's binary, right? So there you go. So this is why, at the beginning of the course, when I showed you that 0.1 plus 0.1 plus 0.1, etc., etc., doesn't actually equal 1, this is the reason. It's because the floating point representation is not precise to, like, it does not have it does not have infinite precision. So, with a finite number of digits, arithmetic operators will lead to rounding errors. Some errors get cancelled, some do not. What about sums of binary fractions? Yeah, that would be fine. That would be fine. Is every floating point number in Python represented using single, double, or full precision? I believe it's double by default. Certainly in these slides we're talking about double precision floating point numbers. That's the 64-bit floating point numbers. Yeah, in C you have to worry, because in C you still have 32-bit floats that are floating around, so to speak. Yeah, 1/2 plus 1/8 will work. I can do that for you real quick. So 1/2 plus 1/8. There you go. That's exact. Ta-da! So sometimes the errors cancel and sometimes they don't. It really depends. So in the case of 1/3, if you add 3 1/3s together, they actually round to, they approximate 1 exactly. However, if you do 6 1/6ths, you don't actually get 1, right? So this can be a problem. Especially this this becomes a problem if you expect to be able to compare these guys to 1, right? In our normal math brains, if you were to add 1/6 to itself 6 times, you should get 1. This should be true. But in computer land, this is false because of floating point imprecision. So does full precision or something like the rational type from Haskell not exist in Python? It does. We're getting to it. We're getting to it, man. It's like, here, we have libraries to help with this. I'm just establishing the problem. And even with those libraries, it's generally speaking a good idea not to you know, get too reliant on them for equality comparison. So, given that equality comparison is kind of broken over floating point numbers, how then do you compare a floating point number to another one to see if they're the same? Well, you have to see within a specific precision. So, if you take the number that you wish to compare them to, right, and you subtract one from the other, then, or I guess I'm going to have to group that. There we go. If you then take the absolute value of that and see if the absolute value is less than some epsilon, let's pick, just for the sake of interest, you know, that small number, then you can come up with true. So basically, you have to pick a very small range around 0, where the difference difference between the two would be small enough to fit inside if they were approximately equal. This is how you perform inexact equality comparison over floating point numbers. Now, you have to be careful when you pick your epsilon, because if you pick it like too loosely, you could include things as being equal that really you shouldn't be considering to be equal. And if you make this too exact, you're going to get a false anyway, because you're not capturing the capturing the floating point inequality. So generally speaking, I use normally around 8 to 10 zeros, and that usually gives a good result. So there you go. That's how you work with floats. We haven't really, I just showed you how to use floating point numbers, but we haven't really defined what they are yet. So, so what is a floating point number then? A floating point number is it's like scientific notation, but expressed in binary, right? So what you do is you take the 64 bits that you have allocated for the floating point number, you chop it somewhere, you make 1/2 the fractional component, and you make 1/2 the exponent, right? Because this is scientific notation. The analog is scientific notation, so we have to have some number of bits which can represent the exponent to the number. Of course, everything is binary here, so rather than have it being like x times 10 to the y, we have x times 2 to the y, right? And everything's in binary. So, all of this has been standardized, right? It was standardized, I believe, in the 1960s or 70s. So, every single computer on the face of the planet, which is compliant with the relevant specifications, must use the same division between the bits allocated to the fraction and the bits allocated to the exponent. Incidentally, the fraction is also sometimes called the mantissa. So, you had an engineering trade-off here, right? If you allocated more bits to the mantissa, you would be able to increase the precision of the number, whereas if you allocate more bits to the exponent, you can increase the range of numbers you can represent. So, like, floating point has a maximum positive and negative number that it can represent. Or it has a maximum positive and negative number. It also has a maximum and a minimum number it can represent. The maximum number it can represent is 1.797, etc., times 10 to the 308. Now, if you know anything about these types of numbers, you'll know that is a very large number, and unlikely that anybody in this universe would be unlikely to need a number that large. Similarly, 2.22 times 10 to the negative 308 is, much smaller than anybody would ever need, probably. If you were to do the number of atoms in the universe, I think that's like 10 times 10 to the 20 or 30 or so. And if you were to do the size of the smallest thing that we have yet detected in the universe, it's only like 10 to the negative 14, I think, something in that range anyway. Anybody who's a scientist in the crowd could correct me on those sorts of things. But yeah, so that's how floating point numbers are represented. And I'm out of time, and I have a class to get to, so if you guys have any questions, please ask them, and I'll answer them quickly. And if not, I'll be seeing you guys tomorrow. So yeah, there we go. I have to go to office hours this week. I don't actually know which tutorial you're enrolled in. Doesn't matter which TA's office hours you go to. Nope. Just show up to whichever one. They're all very nice people. I'm very pleased with the round of TAs I have this semester. It's like uber superstar TAs. Can you go to multiple office hours? Yes. That's why we have so many. If you don't do the assignment this week, it will get dropped, assuming you complete all the other assignments. Yeah, we do drop the lowest assignment, but, you might want to save that. You might want to save your get-out-of-jail-free card. It's up to you, though. Quick question about the midterm. Is the practice exam for the first midterm or the final exam? Practice should be for the... let me take a look. There are a couple, right? Yeah, there's practice test 1 in topic 4, structured data types. That'll give you some questions. It's kind of tricky because, like, the time in the semester where we have the midterm keeps changing, so... Week 7 has a practice test as well, which may have some additional questions which might be useful. Just sort of be selective by topic. And, there are some good recursion questions in the practice 2 test, so you should check those out, but, don't worry too much about the numeric representation type stuff. Just, use some intelligence when you're going through the test. Okay? Where is Basil? Basil graduated, like, a little while ago. I don't know, he's doing Basil stuff now. Yeah, I really enjoyed working with Basil. He's one of my top TAs of all time. I don't have a GOAT TA, well, I don't know. Mark Hutchison is pretty close to a GOAT TA, but, yeah, I definitely have, like, a top 5 TAs I've ever worked with, and Basil's in there, so. Where can I find a list of the tutorials? Ask the TAs where they've been keeping them. I've got to go to my next class. Take her easy, folks. Don't do anything I wouldn't do.